Thank you. And as you said, my name is Laura Mayorga, and I'm at the Center for Astrophysics, Harvard and Smithsonian. And what I want to talk about today is basically some of the work I've been doing in the solar system to define the scientific requirements for direct imaging missions of the future. So as exoplanet scientists, we sort of have these big pie in the sky kind of ideas of all the potential things that can happen out there. And the solar system sort of keeps us grounded. It shows us what the ground truth is, what you can benchmark against, and it's sort of a small slice of the diversity that actually exists out there in the universe. So just to make sure we're all on the same page, I'm going to show this figure again because it was showed earlier this week. But in direct imaging, how it ends up working is that you have a star that is occulted by some sort of mechanism, whether that be a star shade or a coronagraph. And so here you have an example of the solar system where you can't see the sun, you can't see Mercury except inside this occulting mechanism. Venus is also slightly too close, so you probably won't end up detecting it. You can see Earth, its lovely pale blue dot, and then you can't see Mars because it's too small, and then there's Jupiter, and then everything further out from that is outside of our actual field of view, right? So this is an example image that LUVOIR might see, for example, of an Earth or of the solar system at 10 parsecs. Oh, not yet. So the question becomes, how bright is the planet compared to its host star such that we can actually detect it? So reaching for planets like the ones that are in our solar system, we require pretty high planet-to-star contrast ratios. So what I'm showing here is a plot of contrast ratio as a function of on-sky separation, right? Because this is actually what is going to control whether this planet falls into our field of view. And so across the top here, you have a lot of our currently directly imaged discovered planets. The HR 8799 planets are on there. These are self-luminous giants. These are hot, young planets, and so these are normally studied in the near IR. So you can see GPI Sphere. These are ground-based surveys looking for direct imaging planets. And GWS-T, when it launches, is supposed to have a coronagraph as well, and so you can see where that contrast ratio is. But to get down to things like what's in our solar system, we need much higher contrast. So 10 to the minus 9, or lower contrast, I guess. 10 to the minus 9, 10 to the minus 10, you can see where those curves end up falling. But we want to do more than just discover a planet or detect a planet. We want to be able to actually characterize it, say something about what its atmosphere might look like, or for planets with thin atmospheres or no atmospheres, maybe something about what their surfaces actually look like. And so what contrast ratio do we actually need for that? And just to go back to this real quick, what you can see is this is actually from the polar perspective. So these planets are not fully illuminated. Like we see Jupiter, for example, from the Earth only from about fully illuminated about 12 degrees in phase angle, right? So we're seeing partial phases. And so it's important to understand in the solar system, how bright are the planets at different wavelengths, different illumination phase angles, and how that changes depending on their atmospheric properties and through time. But I'll get to that in a minute. So generally, from the recent congressionally mandated National Academy of Exoplanet Science Strategy Report, one of the findings is actually that we need a coronagraphic or star shade-based direct imaging mission. It is the only path currently identified to characterize Earth-sized planets in the habitable zones of a large sample of nearby sun-like stars. And so the recommendations were basically in support of WFIRST, which is going to be the technical demonstration of a coronagraph in space. And then as for the upcoming Astrophysics Decadal, there are two flagship missions in contention, LUVOIR and HABEX, that have coronagraphic and starshade capabilities. This is going to happen. Okay? And we need to be ready for this, because essentially these dots, these pixels or 3 on a CCD, is all the information we're going to get, a single snapshot. And from that single snapshot, a couple of filters you have on it, that spectrum, you're going to try to back out and say something about that planet. Right? So basically you just have the dot on the left, and without having that Jupiter label on it, you need to be able to say it looks like this image of Jupiter that I took from Cassini. Right? Does it have clouds? Does it have storms on it? Does it have weather? Does it have a surface? And that's what we're trying to say. So what I do is I take solar system observations at these various phase angles, and I throw away all of the resolution. I look at disintegrated brightnesses to solve this problem and try to get a handle on the diversity in the solar system and what that might actually appear like in direct imaging observations. So just so we're on the same page again, what I look at is phase curves. And so phase curves right now that we study in exoplanets are generally thermal phase curves, and these are orbital phase curves because the planets are tidally locked, right? So we're always seeing one side, and as it goes, only one side is being illuminated, and it goes around the star, right? We're actually seeing the various phases. Now, because we're looking in reflected light, this is a little bit more complicated for atmospheres because you have the different scattering properties as the photon goes through the atmosphere. We're probing different pressure levels. Okay, so we can say something about the atmospheric temperature, composition, and structure if we are able to analyze this kinds of data. And for terrestrial type planets, this becomes further complicated because maybe you don't have an atmosphere, but then the surface is going to contribute to reflected light signal, right? And so what I'm going to talk about today is the work I've been doing for the Galilean satellites as potential exoplanet surfaces. Okay, and so just to recap, the kinds of phase angles that we're more likely to be detecting with direct imaging is the center 2 here on this diagram, somewhere in that 60 to 120 degrees phase angle, right? The phase angle is that angle between the observer, the object you're observing, and the source of the light. So I've been using Cassini data from the Imaging Science Subsystem, and so if you've never looked at Cassini data before, this is what it looks like. This is 2 images from the 2 cameras on board. This is photometry, so I'm looking at a handful of filters from about 400 nanometers to about 900 nanometers or so. And I basically wrote a pipeline that'll go through the data and identify the locations of the various moons, drop down an aperture, because I'm an astronomer, throw out all that resolution and get a light curve. Okay, so I'm just showing you sort of 2 examples right here. And the way this works is we can cheat in the solar system because I can actually resolve things. So I can look at the variations with phase angle, model that out, and then look at just a little short wavelength or a short phase angle range, in this case 14 to 24, and then look at the rotational variations of the surface. I can go back and forth, I can fix rotation variations, take that out of the phase curve, and basically converge on a proper solution for both. Now the way I'm fitting this is I just take a simple orange slice model. So in this case, we're actually looking at IO. I assume that IO is just an orange, and so I'm doing latitudinal slices, and I'm assuming a brightness for each one of those slices and that it varies with phase angle with illumination in some sort of way. So it's a very simple model, but by doing this, you can get that black fit to the rotational variations up there, and the residuals are on bottom there. And so you can ask the question, well, I just resolved an exoplanet for you with this very rudimentary map. There's, of course, a lot better ways of doing mapping now, if you saw a poster this week on it. And you can ask, how well is that actually representative of the object that we can actually resolve in the solar system? So across the bottom here, I'm just sort of showing you the USGS astrogeological map of Io, and I broke it up in sort of the same longitudinal slices, and so you can see how well that actually matches. Now, this isn't a true apples-to-apples comparison because that geologic map is using Galileo and Voyager data for a bunch of different filters combined and taken at different times, and so it's not truly like exactly the same wavelengths or sort of illumination angles. But it's a pretty good comparison. You can see how well we're doing just by plotting up the slice brightnesses against each other, normalized, of course, and so you can see we're getting the high spots and the bright spots are in the bright spots where they should be, and the dark spots in the dark spots are where they should be. Now I do this for all of the moons in 6 different filters, and then basically I go, well, what if they were actually Earth-sized objects at 1 AU from a solar-type star? What does that look like? I'll give it a minute to come back. Otherwise I'll have to interpretive dance the rest of my plots. So what this slide is supposed to be is, I just wanted to do a quick recap of what we learned from Jupiter. So Jupiter, what I'm showing here on the right is the phase function, so the normalized phase curve for 2 of the filters, a blue filter and something sort of deeper into the red. And so the highlights here for my exoplanet friends is one of the things you can see is that there's a steep fall off at low phase angles, which in the solar system we call the opposition effect. So it is much brighter at low phase angles, and this falls off very quickly as you go off to higher phase angles, right? The red line there is the Lambertian model phase curve of an ideally diffusing sphere. And so this opposition effect, which we see on many objects in the solar system, has never been seen on an exoplanet. And this is for a couple of reasons. One of those being that we don't actually ever see full phase transiting exoplanets. But even outside of that, at this point, I don't think we've actually reached the precision necessary. But we will have the precision necessary to start being able to differentiate between the different phase curve models of exoplanets in the future. So the impact of this, though, we've been assuming very basic phase curves for exoplanets. And in that image I showed you before of the contrast ratios, for example, those curves are assuming Lambertian planets. But what I'm showing you here is that Jupiter is darker than Lambertian at nearly all phase angles. And so if we go ahead and look at what the data is for the Galilean satellites, you see that same opposition effect. So if you want to focus on Io, it's this brown curve here. The width of the shaded bar around it is from those rotational variations that I measured at low phase angles and just extrapolated the whole phase angles range through. And the dotted line is that Lambertian phase curve. So you're seeing the opposition effect on all of the satellites, which we still haven't seen on an exoplanet. You're seeing that they are significantly darker than this Lambertian model that we've been assuming. And so I actually computed the contrast ratios for you. So if you look at a full phase Io in this sort of green bandpass, you require a contrast ratio to detect it of 10 to the minus 9. But you're never seeing it of full phase in direct imaging. So you're seeing something more like half illuminated, which is that 9-degree number. So you need something down to 10 to the minus 10 to detect an Earth-sized Io. Now, that means, though, that detect rotational variations, use those surface inhomogeneities to actually make a map, maybe say something about what your surface composition actually is, or say something about your weather. You're going to need something down to maybe like 10 to the minus 11. And then for Callisto, Callisto's super, super dark, right? You might be down to 10 to the minus 12. So this is a scientific requirement that we need to meet if we're going to be able to study terrestrial exoplanets and actually say something about their surfaces, right? So this is assuming, though, that those low phase angle variations are actually true throughout the entire phase angle range. So I'm showing you on the left what I was showing you before, which is the rotational variations at low phase angles, about 14 to 24, and I've got the little diagram which is above it, sort of showing you what that illumination looks like for a Lambertian sphere. On the right is, I have to cheat a little bit, add a little bit more data into that. So it's from 90 to 140 degrees, but this is basically much higher phase angles. And you can see that the morphology of the rotational variations, the shape of that curve is different. The percentage variations of that is different. So we're not even going to be looking at something that's familiar to us necessarily from the ground. So there's the actual contrast numbers there, right? You need a few 10 to the minus 10 to pick up that rotational variation at high phase angles, 10 to the minus 11. This is still Io, what I'm showing you here. Now, using these planetary science observations in this way has led to a number of open questions and of work to be done. And so this is just sort of one of my laundry lists of what I see as potential pathways forwards and additional ways we can use solar system data to tell us something about what we'll expect for exoplanets, because this is the time, right? We need to prepare for these future direct imaging missions. We need to start practicing our data analysis techniques and actually be able to characterize that data at the moment we have it. And so I'm showing you this lovely picture of Juno, or for JunoCam image of Jupiter. And the first thing you should notice is that, well, since we're going to be looking at planets from the poles, like in that image, it's important to understand the poles of our planets. And then this is to say nothing of obliquity, right, and what Uranus might actually look like in direct imaging observations. And so images like this of Juno with JunoCam and the Cassini end of mission orbits are critical for doing this kind of work. And so that's one potential avenue forward. Honestly, looking at this image, I've designed to throw out all of that resolution, which I know hurts all of us deep inside, and get the light curve from that. Because even though it makes great eye candy, we got to eat our vegetables. Other avenues forward are, of course, models we can use to understand Uranus, put Uranus closer to the sun, global circulation models, of course, for every icy world that basically just gave you a good boundary condition, so you can go crazy. And models for exoplanets. So when I'm not pretending to be a planetary geologist up here, I'm pretending to be an atmospheric scientist. And so a lot of what I do actually is modeling sort of these strange salt clouds and these warm Neptunes and trying to figure out what the reflectance spectra actually looks like. So I have designs to do a lot more work, but of course this is a lot of work, and I think everyone in here has something to contribute. There's no body in the solar system that is off limits for understanding exoplanets. So I hope all of you come away bolstered to go do something a little bit crazy. The real killer in this, of course, I have the clock up there, is that in exoplanets we like to pretend that, stars vary, we can account for that, but we really haven't started to consider exoplanets varying, right? You can imagine I make an observation of a Mars, and maybe it's summer in a hemisphere, and the polar ice caps look a little bit different, or it's in a global dust storm, and I'm like, oh, that planet's really hazy. There's too much aerosols in the atmosphere. It can't possibly, have any good observations. But you're, a couple months later, well, in Mars-year times, right? It clears back up again, you can see the surface. So these are the kinds of things that I think we need to start looking at as well. But secretly, I'm terrified because if Jupiter's pole is actually blue, then that picture from Blue Var is completely wrong, and it should be blue and not red, right? So basic things that we can use the solar system data for, and really say something impactful about the way exoplanets work. So I'm out of time. I'm just going to leave up my last slide if it advances. Okay, there we go. So just to summarize a little bit, direct imaging missions are going to be measuring terrestrial planets, right? These are going to be much darker than the Lambertian model. They're measuring Jupiter-like planets. These are much darker than our basic models have been telling us, and so we really need to hit high contrast ratios to be able to characterize, right? Because that's what we're all really after, and what we all really want to do is say something about the properties of these planets. So that's all I've said. Thank you for your attention.